Hello, this is Jack Jackson. In this video, we're going to be talking about vector motion along a 3D parametric curve. So before you watch this video, you should have watched the previous one in this playlist because it deals with vector motion along a 2D parametric curve, and it's just a lot easier to see these things in 2 dimensions than it is in 3. For one thing, the medium of a piece of paper or a computer screen such as this is actually a 2-dimensional object. So you can't really illustrate what's going on in 3 dimensions on a 2-dimensional display. You can, but it's just not as good. But that being said, if you understand what's going on in 2D, then 3D is a very straightforward and pretty easy generalization of that. So, for example, the position function, r of t, is a vector which goes from the origin to the point on the curve. This curve now is in 3 dimensions, so it's going to have x, y, and z coordinates, all of which are functions of some parameter t. So this is a vector function where the input is a scalar, t value, and the output is a vector, a 3D vector in this case. The velocity vector is just the derivative of the position vector, and it's just done component-wise, just like it was for 2 dimensions. So it's x prime t, comma y prime of t, comma z prime of t. Acceleration is the derivative of the velocity, or the second derivative of the position function. So it's the second derivative of x with respect to t, comma second derivative of y with respect to t, comma second derivative of z with respect to t. The unit tangent vector, just like it was before, is just the velocity vector divided by its norm. The velocity vector is tangent to the curve. That's still going to be true in 3 dimensions. And so that's a pretty straightforward thing. So in other words, it's just r prime of t divided by the norm of r prime of t. I'll show a little bit later in this video that if you take the t vector and take its derivative, and then divide that by the norm of its derivative, you end up with a vector that is normal, that is perpendicular, orthogonal, to the t vector, and it will be a unit vector. Then if you take the t vector and cross product with the n vector in that order, you'll get a b vector, which is called a binormal vector. Of course, that's going to be perpendicular to both the n and the t vectors. So you get these 3, and it turns out to be a unit vector too. So these turn out to be 3 little unit vectors that helps describe where you are and so forth, what direction your motion is. Okay, so let's take a look at this. So that's the same thing here. So here's an example of a curve, and we'll go over what the formula is of this, and I'll show you some different views of it. But I have the position vector going from the origin to a point on the curve. I have the velocity vector, which is the tangent, is a tangent vector going along here. Okay, and that's r prime. And then r double prime, that's the r prime or velocity vector, is the green one. The brown one, brown one here is the r double prime, which is the acceleration vector. And of course, all these vectors are 3D vectors in this case, and the curve is a curve in space. Later on, I'll show you these unit vectors, T and B combinations in a little bit. This is basically from a GeoGebra sketch that I downloaded, and I've used a lot of these GeoGebra sketches. These are when somebody does a good job making one of these, I'll make use of their work, and I want to give a shout out to all the authors for these things. But you can click on that and look at this thing in some detail in 3D. So let's do that right now. So here is the curve. Let me turn some of these things off. You can turn them on and off with these check marks here. And here is the curve itself, and you can take a look and see what that looks like. If you look at it from straight above, it's actually a, well, let's see, let's turn it around. If I can get it going the right way, almost there. That is just the, whoops, that's backwards. Let's see here. Positive, positive. Okay, that way, if I get it turned just right, is the XY plane. I almost had it. I don't know how to rotate this thing around. And then rotate this around this way. Well, that's close. But anyway, there's the, yeah, that's more or less it. So there's the XY plane, and you can see a parabola there. That's the parabola that's graphed over here on this side. So you can see the XY coordinate of that, that red point there. But if you go from the side, let's see, where we let go like this, you're going to get a cubic. Okay, or actually probably going better yet if I turn it from, let's see if I can get it going this way, from this side. Nope. I want to look down. Almost there. Okay, so more or less we're almost there. That's y equals x cubed, because the formula is z of t is t cubed, y of t is t squared, and x of t is just t. So t and x are the same thing, and then the y is just x squared. If you let z be 0, that would be project down onto this parabola. If you let say y be 0, you've got t for x and t cubed for z. That would give you a cubic. So when you see this thing in 3 dimensions, let me just move it around some various different ways, you can kind of see what the thing looks like. So depending on what vantage point you're looking at, it could look very different. And so that's why it's useful to actually, if you could actually build this thing in 3 dimensions, then that would be the best way to look at it. But we can look at it in various ways here. Now, we can also put in the position vector, no matter what we do, and that's going to go from the origin there. And while we're at it, let's show both the velocity and acceleration vectors. And there we have it. So now I'm going to move the point. So I'm going to move the point across here. There, we're starting to come into view, kind of off out of view there. Okay, there we're in view, and you can see the vectors as we go on out this way. Okay, let me rotate it around a little bit. Do it again. Okay, whoa, so where did we first come into view? Yeah, here we're starting to come into view here, and we're going out that way. So depending on where you are on this thing and what view you're looking at, some of these things are easier to see than others. Okay, now these TBN vectors, I'll go ahead and throw those up there as well. Notice that the tangent vector is the purple one here, and it's going in the same direction as the green velocity vector. So I'm going to take away the velocity vector. In fact, I'm even going to take away the position vector. And now you just got those 3 vectors. And notice that they form little right angles. They're kind of like I, J, and K coordinates, but from where you are. Okay, so if you're pointing toward the if you're looking down this way in the direction of motion, okay, depending on how you're oriented, then the normal vector will be, let's see, the t will be in the direction you're going, and the normal vector will be pointed to your left, and then the t vector, the binormal vector will be pointing up then if you're oriented in that direction. Okay, And so you can kind of see those things as we move this around. You can kind of see what happens to them. Let's get a better look at the graph at the thing here. So let's see. Maybe looking down a little bit more from above, and we can see where this thing is going. Let's run it backwards. In reverse. Okay, if we go forward, we're going in the direction of the purple arrow. Okay. Same thing, maybe from a different perspective. Maybe from here. Let's move this enough for it to show up. Okay, we're starting to show up pretty soon. There we go. Okay, so depending on which direction you put this thing to, you're going to get better or worse views of what's actually happening, or you see certain things better from some ways, other things better from other directions. Okay, so hopefully that gives you some idea of what that thing actually looks like. So the formulas for this particular one are r is given by the vector t, comma t squared, comma t cubed. So then it's not hard to find the velocity vector. Derivative of t is, with respect to t, is 1. Derivative of t squared is 2t. Derivative of t cubed is 3t squared. That's pretty easy. The speed is just the norm of that, or the square root of the sum of the squares. So you get 1 squared is 1, 2t squared is 4t squared, 3t squared is 9t to the fourth, and then square root of all of that. Reordered it slightly, putting a decreasing order of powers of t. The acceleration vector is the derivative of the velocity vector. So the derivative of 1 is 0, derivative of 2t is 2, and derivative of 3t squared is 6t. And the unit tangent vector is you take the v vector divided by its norm. Well, we already have the norm, which is the speed, and we have the velocity. Just distribute that, and you get this vector that you see here. For the unit tangent vector, the x component is 1 over the square root of 9t to the fourth plus 4t squared plus 1. The denominator is the same on all three parts, and the numerators are 1, 2t, and 3t squared for the three components. So that's pretty straightforward. To get the unit normal, now things start getting a little nastier, because this is a little harder to take the derivative of these things because you got square roots of whatnot in the denominator. It's not too hard to do, but it's just tedious. Takes some time. I don't have the details worked out here. I'll leave that as a little exercise for you if you'd like to do that. But here's the results you should get. We get the derivative, and then we have to divide by the norm. Now these denominators, it's not coming out very plainly on my thing here. Let me see if I can fix that. Yeah, that looks better. You can see the square roots a lot better this time. So anyway, it's got a square root of in the denominator all the way across on the unit tangent vector. And then you take the derivative, you get a square root here. If you notice, it's the same factor in the denominator here, but it's another factor, 9t to the fourth plus 9t squared plus 1, with that under the square root. And then that's the denominator all the way across. And the numerators are negative t times parentheses 9t squared plus 2 for the x component. For the y component, it's the opposite of 9t to the fourth minus 1. And then the z component is 3t times parentheses 2t squared plus 1. That is a unit vector that's normal to the curve, normal to the tangent vector, okay? And then, which is normal to the curve. And the binormal vector is t cross n, and that turns out to be actually the square root of this other factor, the square root 9t to the fourth plus 9t squared plus 1 is the denominator there in all three parts, the numerators being the 3t squared for the x component, negative 3t for the y component, and 1 for the z component. All right. There's some nastier or longer calculations for this last part. I actually used the TI Inspire for this. I'm going to show you how that looks on the Inspire. I just took bracket t, comma t squared, comma t cubed, stored it in r of t, and then it said done. And if I said r of t, it would come back with that. I also did r of 1, so specifically, if I do that specific 1 vector, that goes to 1, 1, 1 is that ordered triple for that point in space when t is 1. And then I just said take the derivative with respect to t of r of t and store it as v of t. Then I said what is v of t, and there it is. That was easy enough to do by hand, but I have it stored in there now. I can do v of 1 real fast. And so now r and v are functions of t that I can put in inputs, or I can do other things with them. For example, I can do the derivative of the v of t, store as a of t, ask it what a of t is, and there's the derivative there. That's the acceleration function. Take v of t divided by the norm of v of t. Now, I had to be a little careful here because I'm using t for my input variable. I didn't want to use t for the unit tangent variable. So instead of using a capital T here, I just use u. But that is the capital T vector. And u of t is given here. If I had my screen active on my calculator, I could scroll over and see this this third component. But you can see the first two there and the start of the next one. If you take the derivative of that tangent vector t divided by its norm, the norm of the derivative of the tangent, you get the unit normal vector, which I stored as n of t. And again, here's n of t, and that's looks like I'd scrolled over to the middle of it. So that's somewhere in the middle of that one here. If you do the cross product of u and n, you get b of t. And so I stored that there and then asked it what b of t was. Then I can go back and evaluate all those at 1 to find the specific vectors, which you see over here typeset in color, and then here's from the calculator, r of 1, v of 1, a of 1. That's actually t of 1, it's u of 1 in the calculator. N of 1 and b of 1, they have actually rationalized the denominators here. And so that's where all of those came from. And so all of those vectors are illustrated, those specific ones are illustrated on this drawing here. So here's the curve, and this black is the curve here. I've oriented it a certain way, so I think we can kind of see everything. If we go from the origin out to the point, that's the r vector, 1, 1, 1. So that's the point 1, 1, 1, is that red dot. The velocity vector, 1, 2, 3, is this green vector. Its length is the square root of 14, which is the speed. The acceleration is the brown vector here, which is the vector 0, 2, 6. The unit tangent vector is square root of 14 over 4 over 14, square root of 14 over 14, comma, square root of 14 over 7, comma, 3 square root of 14 over 14. That's the unit tangent vector. Notice it's going along the same distance, same direction as the green one, which is the velocity vector. If you're pointing that way, you'll see this one. If you're turned the right direction, you'll see this one out to your left. And then the cross product then will go this way, which should be pointing up. Okay. Okay, so let's see what else we got. Okay, the next thing I want to go over is a dot product rule for vector derivatives. And you get sort of a nice little result that's a kind of a dot product. Well, it's kind of like the product rule for derivatives in Cal 1, but it's a for dot product here. So if we take vectors r and s, let's think of them as vector functions. So r of t is a of t, comma, b of t, comma, c of t. S is a vector function of t, so it's d of t, comma, e of t, comma, f of t. Of course, a, b, c, d, e, and f are just regular old Cal 1 kind of functions, parametric equations for those those two functions, vector functions. So if we want to do the derivative of the dot product, well, first we just do the dot product. So we do that. The way that works is you multiply the components together and add them up. That gives you a scalar function. So a of t times d. So basically you got a times d plus b times e plus c times f. Of course, those are all functions of t. So ultimately we get a scalar function of t and take the derivative. Well, now we could use Cal 1. We take the derivative of each of those three pieces, but each one is the product rule. So it's the first times derivative of the second plus the second times derivative of the first each of the times as we go across. So that gives us a d prime plus a prime d plus b e prime plus b prime e plus c f prime plus c prime f in some order. Now what I want to do now is I want to group it together so the ones that have the primes on the second one, d, e, and f are together, and the ones that have primes on the a, b, and c are together. So grouping those together, we can see that this first group of three is actually a dot product of a, b, c with d prime, e prime, and f. A dot product of those vectors. And the second one is a prime, b prime, c prime, that vector dotted with the vector d, e, f. And of course that means that it's just ABC is R, D prime, E prime, F prime is S prime, and so forth. So what you get is R dot S prime plus R prime dot S. So it works basically like the product rule works for calculus 1. First times the derivative of the second plus second times the derivative of the first. The times is the dot product here. Now I wanted to do that to show you something here on the next page. Suppose we start with a vector that's a constant length. Let's say R is given by x of t, y of t, and z of t, but the norm of R of t is some constant number c. So it's not changing as we change t around. It's that length is staying the same, which means we're tracing out some path on the surface of a sphere centered at the origin of radius c. So the computations we're going to show below will show that the derivative of this vector is going to be a vector that's tangent to the sphere and perpendicular or normal to the position vector. So we're going to use that dot product rule for vector derivatives that we just did on the previous slide. So the dot product, remember, is the norm of that vector squared, but since that norm is the constant c, this dot product is c squared, which is a constant. So if we take the derivative of c squared, we get 0. It's a constant. But c squared can be replaced by r dot r. The derivative of r dot r, according to our dot product rule, is r times r prime plus r prime times r. Well, wait a minute. Dot product is commutative, so both of these are just an r times an r dotted with an r prime. So we have 2 of the r dot r primes. We'll divide both sides by 0, and we see that r dot r prime is 0. The dot product of two vectors is 0 if and only if they're perpendicular. So we set out to prove what we wanted to do. So the unit normal vector. Well, the unit tangent vector is a vector of constant length. Remember, it's length 1. So by the result on the previous page, it is normal, that is perpendicular or orthogonal, to its derivative. However, even though the unit tangent vector is a unit vector, its derivative might not be a unit vector. So we divide this derivative by its norm to get the unit normal vector. So that sort of proves that this vector here, this n vector, is what we say it is. It's a unit vector that's normal to the unit tangent vector. And then this binormal vector is the cross product of those two. Now remember, the cross product of any two vectors is normal, perpendicular, orthogonal. 3 different words for more or less the same thing, to both of the original two vectors. So this binormal, it's normal to two vectors. So this binormal vector, b, is the cross product of the unit tangent vector and the unit normal vector in that order. Of course, cross product, the order matters. If you cross product the other direction, it'll point the opposite direction. Okay, and the cross product of two unit vectors is a unit vector, so this binormal vector is also a unit vector. So the unit tangent, normal, and binormal vectors are all perpendicular to each other. Any two of them are perpendicular to the others. So similar to the I, J, and K unit vectors for the coordinate system. In fact, if you're a particle in motion, you're facing the direction of the motion you're looking at in the direction of t. If you're ordered correctly, n will be pointed to your left, that should say, and then b will be pointed up. So these three vectors, the tangent, normal, and binormal, those unit vectors, those have something to say kind of about what direction we're kind of orienting ourselves. And keeping track of those things can help describe the motion of the object and kind of its orientation as it's going through this motion. So this can help, for example, in helping describe, say, the motion of a spaceship, some kind of spacecraft, or maybe an airplane or something like that, where we're tracking its motion as well as which way it's oriented. Okay, so as you can see, these things generalize pretty nicely from the 2D versions, which we could visualize maybe a little bit more easily, but this also is more general. And you can also see that these are pretty straightforward formulas, although they can get a little messy to compute as they get further into things, particularly the unit normal and binomial. Time you get down that far, the calculations can get a little messy, but it's something we can accomplish.